Welcome back, ladies and gentlemen. We are going to finish up our second unit today by taking a look at some nuclear chemistry. And while this is a little bit different than some of the information we have been talking about previously, I feel like this is a really good place for us to kind of slide this content in and learn a little bit about how, well, nuclear chemistry works. Nuclear chemistry plays a really important role in our lives, particularly with the idea of nuclear power, nuclear weapons, nuclear fission, which occurs in a nuclear reactor, fusion, which occurs as a result of the sun. So lots of different interesting information related to this and a few practice problems that we'll encounter along the way. Hopefully you'll get to our learning targets today, which are you will be able to understand a variety of nuclear reactions and how they take place, calculate the results of nuclear decay, and solve a variety of half-life problems. Some few new vocabulary terms here for you. We got nuclear reaction, transmutation, radioactive decay, alpha particle, beta emission, positron emission, electron capture, and half-life. So let's get started. So far we've been talking about chemical reactions where the atoms of a compound during a chemical reaction are rearranged to form new chemicals. Well, in a nuclear reaction, the nucleus is actually physically changed. This is also known as a transmutation because the atom changes due to the number of protons. So as you already know, the number of protons determines the atom that we are looking at, and if the number of protons is changed as a result of that, then we change the atom at hand. If we look here on the right, we've got two helium atoms that are fused together and end up creating a beryllium atom. And then one below, you've got a beryllium atom that fuses with the helium atom, and as a result, we get a carbon atom. So we've got two protons at the top, two protons at the top, and because they fuse together, we have four protons, which changes the element to beryllium. Same thing down below, we have four protons and two protons, and they fuse together to form carbon, which has six protons. They're a little bit different than normal chemical reactions, but they still show conservation of mass. So if you look at the nuclear notations down below, we have a total of 9 protons and neutrons in that beryllium atom, and 4 protons. And then what we're doing is we're fusing that with a helium atom with 2 protons and 2 neutrons. And so if you look, it works just like a math problem. At the very top, we've got 9 plus 4, and then your reaction arrow, 12 plus 1. So again, conservation of mass still applies here, just looks a little bit different. It's the same with the number of protons as well. We have 4 protons for beryllium, 2 for helium. When they react, they form a 6-proton nucleus, which would be carbon. So the concepts still apply here, and if you take a look at this practice problem, it makes sense. Identify the product that completes the following reaction. So we have a decomposition of polonium with 212 as its mass number and 84 as its atomic number. A helium atom is released, but we want to know what other product is produced from this reaction. Well, working just like a math problem. So we got 212. The reaction arrow essentially means equal in this case. 4 plus blank. Well, do a little bit of math and you'll find that it's 208. Same thing with the number of protons. 84 equals 2 plus blank. Well, it's going to be 82. And so what we do is we set up our nuclear symbol. We take a look at the periodic table and find that 82 is the atomic number of lead, or Pb. And so that's how you would go through and do those types of problems. It's very simple, very straightforward. We just do a little bit of addition and we go from there. So as you mentioned before, some elements are not naturally stable. They have higher atomic masses and maybe they're man-made elements. Well, these will undergo radioactive decay, which releases some of those particles from the nucleus to create a more stable form. As we mentioned, there are several transuranic elements, which means that they're beyond uranium on the periodic table, and many of these are not naturally stable. As a result, they release particles in order to become more stable. So for example, darmstadtium, element 110, decays in about 11 seconds. That's about how long it lasts. And so you look at the reaction here, it decays into meitnerium. The rapid decay continues until the nucleus is stable, so that meitnerium may decay into something else and may decay into something else until it becomes a stable isotope. There are several different types of radioactive decay, and again, these will depend on the circumstances and the element that we're looking at. But the 4 main ones, there's alpha decay, which requires a release of a helium nuclei. So you see that there with polonium becoming lead and a helium atom is released. Beta emission, which is where a neutron is actually converted into a proton. So you see it looks a little weird because it has a beta icon, but there's a negative symbol associated with it. So you have to do a little bit extra math here. So with that carbon 14 that's there on the left-hand side under beta emission becomes a nitrogen 14 because one of those neutrons is converted into a proton, thus the element is actually changed. Beneath that, we have what's called positron emission, where a proton is converted into a neutron. Essentially, it's the opposite of beta emission. So you see there we've got potassium 38 that ends up becoming argon 38 when one of those protons is converted into a neutron. And then there's also what's called electron capture, where an inner electron converts a proton into a neutron. So in a way, it's very similar to positron emission, except that it actually captures the electron instead of emitting one of them. That's why it's on the opposite side of the reaction arrow. And as a result of this, we end up going from silver to palladium because the atomic number has been changed. Let's do a few practice problems to start. First, let's show the beta emission of an atom of copper 60. Well, remember, we need to write these in our nuclear notation. So we're going to write copper, and our mass number is 60. And if we look on our periodic table, the atomic number of copper is 29. Okay? And we're going to be doing a beta emission. So we do definitely need to know what that is. And if we look, we have a little beta symbol, 0, and a -1. So now we just need to do some math to figure this out. So this essentially states that 60 equals 0 plus blank. Well, that's easy enough. That's 60. And 29 plus a -1 equals, well, to make this right, this would be 30. And we need to write our correct symbol over here. If you look at our periodic table, 30 is zinc. And there's our answer. Pretty straightforward. Let's try one more practice problem. Show the alpha emission of an atom of uranium-235. Well, we know uranium. We know our mass number is 235. And our atomic number on the periodic table says 92. Again, we need to show alpha emission. And if you remember, it's essentially the release of a helium nuclei. So we have our atomic number of 4, mass number of 2, and helium. Now we do our math and solve. So this number over here will be 231. As 235 equals 4 plus 231. And then our atomic number is going to be 90. And if you look, that is TH. There we go. Pretty straightforward on how to do these problems, so hopefully you'll have no problem doing them when we start working on these on homework assignments. The next key concept we're going to take a look at is half-life. And half-life is the amount of time required for half of the atoms in a sample to undergo some form of radioactive decay. So if half-life is 10 minutes and a 20-gram sample will have 10 grams of the original element left in 10 minutes and then 10 grams of the other material. So if we take a look at the graph on the right, we have decay of cobalt-60. We start with 10 grams and then over one half-life we have 5 grams of cobalt-60 left over. The other 5 grams has become some other type of chemical. Now, one other thing to consider is the amount of time a half-life takes. So if we look at the example here, for cobalt-60, the half-life is 5.27 years. That half-life is going to differ based on the chemical element that is undergoing radioactive decay. We can do some practice problems with these. Let's take a look at some. The half-life of polonium-210 is 138.4 days. How many milligrams of polonium-210 remain after 415.2 days if we start with 10 milligrams? So the first thing you see here is that there's a lot of information in this problem, but if we break it down, it shouldn't be too difficult. We know the half-life is 138.4 days. And we know that we're experiencing a time of 415.2 days. And we start with 10 milligrams. So we start with 10 milligrams. And we know the half-life is 138.4 days, and we go for 415.2 days. So we need to determine how many half-lives are taking place, because what we want to know is how many milligrams of polonium-210 remain. So basically we want to take this down to the completion of all of the half-lives. And in order to do that, we need to know how many half-lives there are. So in order to do that, we'll take the amount of time we experience, and we're going to divide that by how long each half-life is. That will tell us how many half-lives we undergo. So if we do the math here, we end up with 3, meaning we undergo 3 half-lives. So if we undergo 1 half-life, we're left with 5 milligrams, right? Because it's half the amount of what we started. If we undergo 2 half-lives, we have 2.5 milligrams of polonium-210. And if we undergo 1 more half-life, we have 1.25 milligrams left. Okay? So like I said, it's all about learning and thinking about what information do I have, what do I need to solve, and then what steps do I need to take to get there. So underlining, highlighting, circling, all of that's going to be very, very convenient for you when you start going through and solving these problems. Let's look at the next question. If starting with 80 grams of radon-222, how long will it take to decay into 1/4 of the starting amount if the half-life is 3.8 days? Well, let's take a look at the information that we're given. We have 80 grams of a substance. We know that we need to decay into 1/4 of the starting amount, and the half-life is 3.8 days. The question is asking how long will it take to decay? Well, we know that we need to get it into 1/4 amount of the starting amount. And since the half-life takes away half each time, and we want 1/4, think about that. How many halves would we need to get into 1/4? Hopefully, you can see that that would be 2 half-lives, right? Because each half-life is a half. If we go a second half-life, that's another half. Half times a half is 1/4. So since we only need to go 2 half-lives, we know that each half-life is 3.8 days, and we want to know how long it takes. We're simply going to take 3.8 days and multiply that by 2, thus getting our answer 7.6 days. Now, this question was a little bit tricky because it gave you some more information than you actually needed. It told you we were starting with 80 grams, and we really didn't need to utilize that in any of the problem that we went through and completed. So be aware of that. Just make sure you underline the information that's given to you, circle what you're trying to get, and the problem should be relatively easy. But take it one step at a time, and I'm sure you'll have no problems whatsoever. So hopefully everybody understands that nuclear reactions impact the nucleus of an atom, and that radioactive decay leads to more stable nuclei over time. And half-life is the amount of time it takes for 1/2 of the amount of a substance to decay. Again, hopefully you were able to meet the learning targets for this video. This is the last video for Unit 2. We're going to dive into some awesome modern atomic theory in our next unit. Have a great day, guys. We'll talk to you later. Bye-bye.